Hello, welcome to a quick overview of the highlights of our IsoBERT project. My name is Rishi Jha,
I'm Kami Hata.
and let's get started.
State-of-the-art deep textual analysis models and smaller NLP projects both could benefit from smaller sentence embeddings. There's a lot of work being done optimizing these sentence embedding models, but another approach, one that we are taking, is to reduce the dimensionality of the output embeddings from DistilBERT.
The two main ways to do dimensionality reduction are linear and nonlinear. Linear dimensionality reduction tends to be a little faster, while nonlinear dimensionality reduction focuses more on the internal geometry of the data. Here we're focusing on DistilBERT embeddings, and we believe that text has some sort of internal geometry. So the question remains, does DistilBERT keep track of this internal geometry? And we have some preliminary evidence to believe that it does. Here on the left, we show a nonlinear dimensionality reduction in IsoMap. And you can see the Miley Cyrus lyrics in orange tend towards a linear shape, while the Microsoft Service Agreement is more scattered. And on the right, using PCA, since it's a linear dimensionality reduction, you don't see as much shape in that. There's no reason to believe that a priori IsoMap is the best. Internally, we figured out that IsoMap performed the best on our data set, but there are other nonlinear reduction techniques, namely kernel PCA and locally linear embedding. As mentioned earlier, we found that IsoMap performed the best in our tests, and we've shown the algorithm here on the screen. And we believe that a lot of the reason IsoMap performs better than LLE, for example, is that it focuses on the entire geometry and the entire data set. Whereas LLE, locally linear embeddings, focuses a lot more on select neighborhoods. This leads us to our methodology. In this project, we started with the 768-dimensional BERT, and then ran a 64-dimensional PCA to create our large PCA embedding, another 16-dimensional PCA to create our small PCA embedding, and then a 16-dimensional IsoMap to create our IsoBERT embedding. And you may ask yourself, why not use IsoMap directly from DistilBERT to IsoBERT, 768 dimensions to 16 dimensions? And empirically, we found that this takes far too long, and the 64 dimensions of large PCA encapsulates nearly 80% of the variance of the original DistilBERT, and we found that to be sufficient.
To evaluate our models, we chose 4 different datasets, 3 of which were text classification and 1 sentiment analysis dataset with a varying number of classes. Through empirical testing, we found that the optimal number of components for large PCA was 64. For IsoMap, 16 components with 32 neighbors, and for small PCA, 16 components. Our downstream model consisted of 2 fully connected layers with a hidden dimension of 32, and this is the model that we used for our base case of logistic regression. In our final results, we found that compared to small PCA, IsoMap, which had the same number of components, averaged 1.1% better test accuracy across the 4 datasets. Compared to logistic regression, IsoMap had a 48-fold reduction in dimensionality, but only performed 1.7% worse in test accuracy. And finally, even though the IsoMap dimensionality reduction takes longer than the linear dimensionality reduction, we found that it converged faster in all cases. Here are some selected embedding graphs from our tests. We can see that on the SMS spam dataset, IsoMap found a pretty clear distinction in shape between the 2 classes. And on the AG News dataset, the large PCA model found some difference between the different classes, but not quite as clear as on the SMS spam.
And finally, during our project, we found a couple of directions we'd like to continue research on. The first being comparing the DistilBERT reductions to reductions on other transformations like BERT or XLNet. And the second would be to try different IsoMap flavors. There are a couple of other IsoMap algorithms that seem to perform better on some data sets. And finally, try dimensionality reduction that is aware of the model's labels. All of our dimensionality reductions were unsupervised, and we believe that a supervised version of this may perform better. And thanks for watching. And if you have any other questions, feel free to reach out to us or check out our website, and we'd be happy to help. Thanks.